Oh, hello everyone. Welcome to week 8 of this tutorial session. So this week, the topics that were covered were mostly some of the heuristics that people use when training neural networks, right? Like how do you initialize the neural network? How do you uh, check or how do you test which activation function to use? So this week covered four basic aspects of these of training neural networks. So we'll wait for a few minutes if some other people will join. Till then, we can discuss if you have any questions for this week or if anything from last week. So yeah, let's start. Are there any questions from this week? Is there anything you'd like to be clarified?
Sir, it's better. Can you repeat the steps?
Okay, sure. So the first thing that was covered uh, this week was the concept of pre-training. So basically, whenever you are working with machine learning models, so there are two stages, right? You first of all train the model, and then once you train the model, you learn some weights from that, and using those weights, you test the performance of your model on unseen data or the test data. So what is pre-training then? So uh, in one of the previous weeks, we discussed autoencoders, right? So autoencoders. So what were autoencoders? Basically, you are given some input X, right? And then you pass it through some neural network or some uh, hidden layers. You get some representation of X. Let this be some H, and then using a decoder, you try to learn this X, right? So that means your input is X, your output is also X, and you're trying to learn something. You're trying to minimize this loss, right? So your loss was basically uh, Xij, and suppose the prediction is X set Ij. You're trying to minimize this loss summation Ij. So what this was trying to do is given some input, you want to learn some representation of the input, say h, such that using h you can get back the same x that you had as an input. So for example, suppose you input some image of a cat, right? You have some image of a cat, you learn some representation. So maybe this cat is 28 cross 28, that is a 784 dimensional image. Now you want to learn some hidden representation of the cat. So maybe you are learning some 100 dimensional representation of the cat. Now using this 100 dimensional representation, you want to get back the original cat image. So you want to get back the original, say 28 cross 28 image. So once you train this network, so what will happen? You will give this image as input, and it will during this feed forward it will compute some h, which is the hidden representation, and then it will output something, say x hat. So your true label in this case is x, and your output is, say, x hat. And then it will try to see what is, so suppose I'm saying this is a squared error. It will try to see what is the difference of your predicted, or difference of the image that you reconstructed with the true image. So that will give us some loss, and using this loss it will again back propagate. And then once you halt this process, the result that you get is this loss will be small. That means x, the x set, the output that you reconstruct, will be almost same as the input. So that means the age that you learn is a good representation. So age, which is also called as the latent representation. So once your if your loss is small, then h is a good representation. So by good representation, I mean that uh, suppose you want to have a classification problem. Suppose your problem is given an image. You want to classify whether the image has a cat or whether the image has a dog. So I'm saying these, I'm giving this example of image based instances. You can also take some other, maybe you can take language data, or you can take speech data, and so on. So for simplicity, I'm just saying that uh, you have some image data set and you want to classify whether that image contains a cat or a dog. So now let us say that we have that encoder and we have that hidden representation h, right? That we take from this autoencoder that we have. Now using this hidden representation, or using this latent representation, we again pass it through some series of layers, and then maybe because it's a two class classification, you can also pass it to through a neuron, and then we can get a prediction whether it is a cat or a dog. So quick question. So this is a binary classification problem, right? So this is a binary classification problem. So what should be the activation function of this one? Anyone? So basically, you are given some input. Say now you have this h, and now you want to decide whether this h is a representation of a cat or a dog. So that means you have to decide on two classes, right? Whether it is a class 0, say cat, or whether it is a class 1, which is, say, dog. So that means you have a two class classification problem. It is a binary classification problem. So what type of activation function is useful when we have to decide between two, when we have to make a decision on a two class classification problem? You can type in your answers in the chat or you can unmute and answer. So till now you must have seen only a few activation functions, right? So anyone, if it is a two class classification problem and you have to give a 0 or 1 answer, what sort of activation function is required? You can type in your answers also. Yeah, right. Sigmoid. Yeah, good. So this was just a because mm, if, because you must have seen in your assignments, this is a type of these are the type of questions that are asked. So you should these things should be clear, right? When to use what type of activation function and so on. Okay. So this is a two class classification problem. So then you will use a sigmoid function. So sigmoid basically tells you 0 or 1, right? So if it is if something is 1, you say that your image has a cat. If it is 0, you say that your image has a dog, right? As simple as that. So so here we see that once we have some hidden representation that we learn using some autoencoder or by training some autoencoder network, we can use that hidden representation for learning or for downstream tasks like classification or regression. Now, so in the lectures, the professor said mentioned that the deep learning methods were not that popular because the losses never converged. So what we mean that during the training time, the training losses were not getting small. So it will go to maybe it will start at 100 and then it will go to say 10 and then after 10, even if you run 1000 or 10,000 epochs, the loss will not decrease. So in 2006, people came up with this concept of pre-training. So what they did was, so we saw that for autoencoders, using the same input as the target, you can learn a good representation of the input. So suppose you have a network with many hidden layers, right? And I want to learn the best hidden layer possible. So basically, I'm saying is you have some input here, then you have some hidden layer here, say H hidden layer 1, hidden layer 2, hidden layer 3, and then you have some say some output layer. So this is your input layer and this is your output layer, right? And earlier what we are doing, using the original input as a target, we are learning the best representation of the input. But now in what people did was, no, we don't want to learn only the best representation of the input. We also want to learn the best representation of each of these, right? So basically, we want to learn the best representation of H1. You want to learn the best representation of H2. You want to learn the best representation of H3. So for this purpose, what people did was they took this autoencoder idea and then they placed an autoencoder in each of these layers. So for learning H1, we have some autoencoder. For learning H2, we have another autoencoder. For learning H3, we have another autoencoder. So how does that work? So basically for H1 we saw, right? Suppose you have your input here and you have your output, or output is basically say, okay, let me say that, let me represent input by X, right? So you have your input here, and in the output you also place the same X, and you learn some hidden representation of it. And let us say this is H1, right? So basically, first of all, you are just learning the representation in the first layer by using the input in both the input as well as the output. So again, one more thing. So this was said to be an unsupervised pre-training. So what is supervised? Can anyone say what do you mean by supervised? What do you mean by unsupervised? So basically, whenever we are doing machine learning, there are two broad areas. Yes, yeah, thank you. So as Akhil and Shari said, in supervised learning, your labels are already provided to you. So that means if you're talking about supervised learning, you have your X, which is the input, and you are also given some Y. So Y is your output. So using X, you predict some, say, Y hat. You compare that Y hat with Y, and then you back propagate and learn your weights or whatever parameters you have. So that is a supervised learning because it is supervised by the labels that we have. Now, when I'm saying unsupervised, it means that these data do not have any label, right? So take this example of an autoencoder. Your input is X, your output is also the data itself. There is no label, right? So that is why this is termed as an unsupervised learning. So yeah. So now given this okay. So given the input X, if we uh, have a hidden layer H1 and the output as the image itself, so then we learn a good representation of H1, right? So that is what we saw for autoencoders. So suppose I am using some autoencoder here, say AE1, right? Now I also want to learn a good hidden representation for H1. So see, this H1 is a good representation of X, right? Because you from X you get H1. So H2 is a good representation of H1. H3 is a good representation of H2 and so on, right? So now using this same autoencoder idea, suppose I also want to learn a good representation of H2. Say I want to learn H2. So now we know that H2 is a good representation of H1. So what should be the input? So suppose I'm using an autoencoder. What should be the input of H2? So what should I have here? So this is my input. This is my output. Yeah. So we'll have some H1, right? Here I'll have some H1, and similarly, what will be there in the output? We'll have H1, right? So basically, you are also carrying over this autoencoder idea to the next layer. So suppose I say that this is some autoencoder AE2. So basically, what we want is given the H1 as input, we want to learn a representation of H1 using the H1 as output, right? Now we'll get to learn H2. So similarly, if we also have some AE3, we have some AE3. So what the input of AE3 will be H2, the output of AE3 will be H2, and it will learn H3, which is a good representation of H2. So finally, we'll have these. So finally, once we complete this, we will get good representations, good H1, H2, and H3, and then use them for training the network. So basically, you have your input, you have your hidden layer H1, you have your hidden layer H2, H3, and then your output. So now this output is the label that you have. Say for example, if we want to decide what is whether the image contains a cat or a dog, so this output is that y that you have. So take care that in autoencoders the output is the input itself. So if you have x as input, you are taking the x as output, and that is unsupervised. But now when I'm talking about training a neural network, I'm talking about a supervised training of neural network. That is, you're using the y itself. So because you have already learned some good representation of H1, you have learned some good representation of H2 and also H3. Can the so the people, I think, uh, so there are a group of people who are working on it, and they wanted to see if this helps, right? So now again, now you do your normal back propagation and forward propagation routine, right? So if you have X, you forward propagate or feed use the feed forward algorithm to get some prediction Y hat, say, then compute the loss, and then you back propagate it and output the, or sorry, update the weights. So this is your, this this is called a fine tuning algorithm. Fine tuning means you already have some you have learned some weights according to get something such as H1, H2, or H3, and now you are again fine tuning it by looking at the label of that input that you have. So people found that this actually helped uh, solve the convergence problem, or not solve exactly, because earlier the losses were not decreasing. The training losses, like we discussed, the trailing loss would go from 100 to 10, but it will not decrease more than 10. So now people saw that, well, if you are having, if you have some good initialization here, so that means that results in losses that are all that are very small. It could even go to zero. So this technique was very helpful for them. So what exactly are we saying here? So this is all fine that we are trying to learn something, but basically at the end of the day, this is a gradient descent algorithm, and we have some weights as initialized, and now we are saying that we learn some good weights beforehand, and then after that we try to learn the label, or try to learn the weights, so that we get a good, or good prediction in the output level. So basically what we are saying is that earlier the weights were randomly. So suppose my loss function looks something like this, something, this is bad, something like this. So this is a non-convex loss function. So by non-convex, I mean that, so your aim of your gradient descent algorithm is to go to zero loss or the minimum loss. So a function is minimum when the gradient at that step is zero, right? But since this is a non-convex function, you can see that the gradient is zero at this point, the gradient is zero at this point, it is zero at this point, it is zero at this point. So this is a problem with non-convex loss functions. So basic non-convex means that there can be multiple minima that you have. So if some gradient descent algorithm comes and finds that it has a zero slope, zero gradient at this point, it will think that that is the minimum that they have, minimum that can be achieved, and it will not update the weight further. But the optimal weights were at this point. But because the gradient or because the algorithm found that the gradient at this point is zero, it will just say that these are the best weights that we have. But whenever you're doing unsupervised pre-training, you already have some information about the weights that the model should have, right? So that means the uh, the algorithm will see that, okay, I should start from this point because I already know what the weight should be so that I get a good H1. I already know what the weight should be so that I get a good H2 and also a good H3. So using this, I'll just start from there. So for example, in this case, suppose the algorithm says algorithm has been pre-trained and it says that okay, let me start from here. So this we get this configuration of weights by because we it is possible that we learned good H1, H2, and H3 because the weights have been initialized to this point. And now you can see that this is a very good point to start your gradient descent, right? Because now it will actually help you go to the global minima. You will not face a problem that, so suppose we started here, right? We started here, and if we get to this point, it may be that it says that, oh, this is a zero loss, zero gradient surface. I think this is the best thing to have, and I will not go further from here, and it will not, the your function will not optimize further. But now because we saw that in order to get good representations H1, H2, and H3, you already have some information about the weights. So it basically gives us a good initialization. Like this could be possibly a good starting point for the weights of the neural network. So now if I start my gradient descent from here, so it will most probably come to the uh, exact I mean to say the global minima that they have. So this is the global minima of the non-convex function. So if we look back at the concept, so what it says is that we are restricting the weights to be at certain points. So if we did not pre-train H1, H2, or H3, and we are just given some X, we are given some Y, and sorry, we are given some Y, and you have H1, H2, H3, and let us say that H1, H2, and H3 are not pre-trained, but you are just back propagating from Y and then pre-training and then training this, updating this during back propagation. So then you do not have any information about what a good H1, H2, or H3 should be. But if we do some unsupervised pre-training, we have a good information of what H1, H2, H3 should be. And because of that information, you know that our weight should be somewhere around this. And now I say that when I'm doing fine tuning, let me start from this point, and then it helps us to get to a good global minima. So this is exactly the type of concept we are discussing last week when we discussed regularization, right? So what does regularization saying? So in regularization, you have a loss term plus some regularization term, right? So if you remember, for MAC loss, your loss curve was something like this, right? And your regularization curve was something like this. My drawings are not smooth, but get the ID, something like this. And if we did not have the regularization part, suppose we did not have the regulation part, so this part won't be there. So then you will just say that okay, this is the minimum that I have. But if we have the regularization part, you will have to say that okay, my loss, my parameter that I learned, it is not at the global minima, but it is at this point which intersects or which satisfies both the loss and the main loss and the regularization curves. So regularization basically says that okay, I don't want to have to look at all of the weights. I will only look at weights in a specific region. So that is what is happening in this case as well. We are not looking at losses, weights that start here. We're not looking at weights that may be here. Because of the fine tuning process, we know that our weight should be here, and then we're starting from this point. So because of this, you get some loss, good training losses using this unsupervised uh, pre-training type of methods. So this was the first lecture. So the next topic that was covered was better activation functions. So yeah, any doubts on this, on the discussion that we had? If you have no doubts, you can just type no. Okay, good. So the next topic that was discussed was that of activation functions. So again, I'll repeat an example that was covered in the class. And so you have some neural network here. I think I also covered this example in an earlier tutorial, but okay. So you have some input here. So let me say I have X here. I have some hidden layer here, H1, H2, H3, and then some Y. And suppose there are no nonlinear function, and by that I mean uh, we just have some weights here. We have some weight W1 here. We have some weights W2 here, W3 here, and some weight W4 here. So now if I write H1, H1 is basically your W1 times X. H2 is basically your W2 H1. This is W3 H2. This is H1. And finally, this is your W4 H3. So that means Y is W4 of W3 of W2 of W1 of X, right? So that means we can write this as W4 times W3 times W2 times W1 times X, right? So now this is a matrix, this is a matrix, this is a matrix, this is a matrix. And if you don't have any nonlinearity here, you only have some matrix weight matrices that we want to multiply with the input. So that whole output can be written as a product of these matrices and X. So the product of your matrix is basically another matrix Give me a second. Excuse. Yes. So basically, what I'm saying is that these are your different weight matrices that you have, and you are taking a product of these weight matrices, and you get back another matrix, say WX. So this is same as saying that instead of a multi-layer network, you have some X, and you get back Y by multiplying with some W. So you lose the advantage of your multiple layers of the neural network, right? So just doing a matrix vector multiplication. So that is why we have this concept of activation functions or the non-linearities. So these activation functions are also called non-linearities. So you start off with we started off with activation function a few minutes ago, which has a sigmoid activation function, right? So how does the sigmoid activation function looks like? So your sigmoid of x is 1 by 1 plus e to the power minus x, right? So this basically looks like this is your 0, and say this is your 1, and it is something like this. So at 0 it is 0.5, and so on. So as you can see, suppose hmm, suppose your so let us say I'm talking about sigma of some wx, say, right? And now if wx is very high, say I say that wx is say 100. So if wx is 100 and sigma of wx is 1, right? If sigma of w and if say wx is same way, if wx is minus 100, then wx sigma of wx is 0, and so on. So when we are doing gradient descent, so what is the update step of gradient descent? So I'm talking about the update step of gradient descent. So you have some weights at t plus 1 iteration. You have the weights at t minus some learning rate times wt, right? Now in this case, when my sigma when wx is 100, so if wx is 100, it will lie somewhere far away here maybe. So what is the gradient in this case? Anyone? What is the gradient and wx is very high? Can you type it in the chat? No, it is not one. The gradient is 0 in this case, right? Because you are just this is just a 0 slope. Give me a second, excuse. Yeah. So as you see, the slope at this point becomes almost 0 in this case, right? Because you have just a flat line in this case. And similarly, if wx is very small, so then also your slope becomes very small in this case. So that means your gradient of wt is, it almost goes to 0. So that means when we come here, your wt plus 1 is almost equal to wt. That means you are not updating anything, right? Because your gradient goes to 0, this quantity goes to 0, and you are not updating anything at all. So your gradient descent in this case is not working at all, right? So then there was another problem, that this has this exponent computation. So if you talk about computing the exponent, so that requires a lot of terms there, and so it is also computationally very expensive. So these are two problems that we have with nonlinear or this sigmoid function. Another nonlinearity that we had was the tan h function, right? So tan h function is same as the sigmoid function, but the range is a bit different. So your sigmoid function was between 0 and 1, and this range is between -1 and 1. So we have 1 here, we have -1 here, and it is something like this. So here also we have the same problem here, right? So if our wx is large, the gradient here goes to 0. The gradient of w goes to 0. And if our wx is sorry, and if our wx is small in this case, your gradient of w goes to 0. So here also, if we do some gradient descent update, your wt plus 1 is almost uh, close to the weight that you have. So these are two problems, and again another one is that you have this computing this 10h function is hard. Hard in the sense that it is expensive, because you have to look at a lot of terms when you're doing it on a machine. But one thing we saw is that when we're doing this unsupervised pre-training, right? So we saw that if our initialization is good, then it is possible to get to a good training loss, right? Even zero training loss in this case, right? So that means even if we have this, so that means there may be some activation function which helps us get to that. So we face these problems of, so this is basically termed as vanishing gradient. And this term will be useful in a future lecture as well when we are talking about recurrent neural networks, RNNs. So this is the problem of vanishing gradient. So using different, so people came up with a different activation function called as ReLU. So you must have, if anyone has worked in deep learning type of algorithm, he or she must have come up on this. So this is called a rectified linear unit. So rectified linear unit, what it does is, it is defined as, so suppose you have some input x, So ReLU is basically your max of 0 and whatever x that you have. Right? So if we look at it in a, if you try to plot it, so basically it says that if something is less than, so suppose this is 0, if something is less than 0, your ReLU of that is also 0, and if something is greater than 0, and so that means it is whatever value that you have, right? So now this solves a very important problem that we had. So what problem we had was that if Wx is very large, right? If Wx was very large for say 10h or sigmoid, we had this problem of vanishing gradient, right? Like the gradient goes to 0. But now we don't have this problem. If say Wx in this case is say 1000, so what will be the gradient at that step? What is the gradient at that step? Can anyone type it? Yes, the gradient will be 1, right? Because it is just a straight line. So the gradient of anything here is 1. So we don't have the problem of vanishing gradients anymore, right? So now whenever we're trying to do a gradient descent update, it is basically your WT minus some some non-negative, some non-zero gradient that you have, and now it works fine. So whenever I think CNN and CNNs will also be covered in the next few classes, I guess. So whenever you're talking about CNNs, this ReLU will be quite helpful in that case. This rectified linear unit. Instead of the sigmoids that you have seen till now, you'll have this ReLU. And implementing ReLU in Python is also very easy, right? So basically, suppose you have some vector, say vector, say I give you a vector 5 minus 3 2 minus 1 and say 0. So suppose this is some uh, some, I don't know, a that you have, and if I just say the ReLU, what is the ReLU, ReLU of a? So can somebody say what this is? So whenever I'm talking about activations, I'm talking about element wise. That means you apply that activation to each of these elements. So what will be ReLU of A in this case? Anyone? So ReLU is basically, yeah. Good. So this is 50200, right? Yeah, thank you. So implementing this is very easy. So earlier you had this 10h, you had this logistic or sigmoid function, and they required the computing this e to d something, which is expensive. But now you basically compare each element and then you output whether it is, if it is positive, you output the same number. If it is negative, you make it 0. And so if I try to compute the gradient of this, basically because for ReLU the gradient is 1 or 0, so my gradient will be 1 0 1 0 0. So implementing ReLU is very easy. So there are still some problems because heuristic functions, right? There are no guarantees of why this works, but people see that in experiments these things give good results, so people use it. But because there are no such guarantees, there are still some problems. So one problem that people have seen is that if at some point your neuron dies, and by dies I mean to say is that suppose for some you have some neuron here and you have some inputs here, and suppose the input is something like w1x plus w2x plus w3x, oh sorry, x1 x2 x3 and x3 plus say plus some b that you have. And if b is a very large negative number, because you are, if you randomly initialize b, so b may be, it may be a case that b is very large, so then this whole things, the value of this thing becomes very negative, and value of negative becomes 0. That means this neuron dies. Now whenever you are doing back propagation, right, because this the value of okay, another important thing, you see that so take this example, the gradient of this value of a is 1 0 1 0 0. So whenever you are doing back propagation, so when I'm writing this in terms of vector, it means that this is a neuron, this is a neuron, this is a neuron, this is a neuron, this is a neuron. So this is a vector of 5 neurons. Each coordinate represents a neuron. So whenever you're doing back propagation, so you'll have some connections here and then like this, right? Again here, here. So suppose you are suppose you are back propagating through this neuron, because this is one, so this back propagation will go through here, right? And then it will update the corresponding weights. But suppose you come to this point 0, right? It will come to here and it will say that, it will see that the gradient at this step is 0, so it will not update it because this is 0, right? There is no point going backward. So what happens then is that if at some point a neuron dies, that means the value of that becomes 0. So that neuron will never be updated because the gradient is already 0, and that neuron becomes useless forever. So so neuron uh, becomes 0 forever. So that is a problem with ReLU, and we have that problem because whenever something is negative, it becomes 0. So then people came up with different variations of ReLU, like there is leaky ReLU, there is exponential ReLU, or something called as GELU, and those are different variations of ReLU. And those are basically, they say that whenever your activation becomes, or pre-activation becomes less than 0, you don't make it 0, you just say that it is something like this. So you have this thing remains same, but here you just say that we have some small value instead of 0, because if we have a small value here, this gradient here will not become 0, so that means it will be updated and something will be corrected. But for practical sense, for simple architectures, so if you are working with CNNs or images, then ReLU works just fine. So this is it about activation functions. Any question? Any question here? Okay, good. No question. So the next thing that was discussed was the initialization techniques. So you have your, as usual, you have your neural network. I'll just uh, draw this neural network. So something like this. You have your connections here and so on. And suppose what I do is, as you have this W1, W2, and so on. So suppose this whole matrix is W1, this is W2, and some matrix here is W3, right? And I say that all of these are zero. W1 equal to W2 is equal to W3 are zeros. By zero, I mean that W1 is a matrix of all zeros. W2 is a matrix of all zeros, and so on. Now, what happens in this case? So suppose I have some input x1. So suppose this is x1, x2, x3. Suppose I have a three-dimensional input, and I have some pre-activation here, which is say h11. So h11 is basically w11x1 plus w w12x2 plus w13x3. I have not shown these weights here. Yes, right. X3. And because these things are all zeros, these things are all zeros, so h11 becomes 0. And similarly, if I write, say this is say h21, h21 becomes 0, h31 becomes 0, and so on, right? So now, because each of these hidden layers becomes 0, even if you are doing gradient descent, or even if you are doing uh, uh, sorry, not even if, whenever you are doing gradient descent or whenever you're doing back propagation, it will see that all of these are 0, so there is nothing to update, right? So it will not update anything. So initialization with all zeros is a bad idea. It's a bad idea. So yeah, so even if it gets updated, another problem will be that it will see that each of these weights are the same. So whenever it is training or whenever it is updating the weights, it will just make sure, it will just see that the weights are all same, because they started off at 0 and they will get the same level of update. They will not change much, right? And so if the weights are same, none of these features will be much different, right? This will get the same weight, 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 and none of these weights will be different. And so there is no, there will be not much learning to do, because all of these weights are going in the same direction, or they will learn the same values. So initialization with zeros is a bad idea. So how about the case when instead of zeros, I will say that each of these W1 IIIJs are the same value. Let me say each of these WIJs is say 5. Is this a good idea or is this a bad idea? What do you think? So initialization with zeros is bad, is because each of these weight will learn the same or will be updated by the same amount every time, and each of these weights will behave the same because it is all zeros, right, initially, and you'll get the same gradient. But how about if I initialize it with the same value, but which is not zero, which is non-zero, but still these are all the same value? Will it make a difference? So it will not make a difference, because again you get the same issue here, right? So initially these are not zeros, this will have some value, this will have some value, but after some time it will see that okay, all of my weights are same, so it will update them by the same amount, and again you will have the same problem, right? All of these neurons will start behaving similarly there, so there is no use having this many neurons at all, because they are behaving the same, and again you will not have much learning to do. So that is why people started to come up with different initialization schemes. And the one scheme that was discussed in the class was, uh, I think it was used by Jan Lekun, if I am not mistaken. But uh, so he said that, so there are two terms now. So suppose my input, so suppose I am at a layer which has dimension say 3, and I am at a layer which has dimension say 5. So quick question, what should be the dimension of W here? What should be the size of the or dimensions of W matrix, so that I can go from 3 dimension to 5 dimension? Anyone? Yeah, what should be the not 5? So this is a so W will have some rows and columns, right? So what should be the number of rows? What should be the number of columns of W? So this will be connected to each of these. Similarly this, and similarly this, 3 cross 5, right? So that means if I have some HCl, and I do HW, H is basically your 3 dimensional vector, right? And suppose I write HW, so it becomes something H prime, which is basically your 5 dimensional vector, right? Hmm. So the thing to the thing, so this was just a quick question. So there are two terms that are generally used. This term, the input dimension, or the dimension that is on the left hand side, is called the fan in, and this is called the fan out. So basically, so because we saw that initializing with zeros is a bad idea, initializing it with the same value is also a bad idea. So what people do is, okay, let me initialize it with some random variables. So if you have worked with NumPy, there is this library called, or there is this package called random, and it has something called randn, and you just have to give the shape of the matrix that you have. So I will give the fan in amount, the fan out amount, and then so in the lectures you can go back and see, we want the variance to be 1, because otherwise you have a problem of exploding page. Exploding means as we increase the number of layers, the value of the activations, the h sizes that we have, it may become very large, because you are just accumulating values one after the other. So that is why, to prevent that from happening, we make sure that the weight should not have high variance. It should have a variance of 1, and that works out if we have some uh, some normalization factor, so basically a root of fan in. So that is one initialization scheme that is very popularly used. Again, this is there is no theoretical guarantee that this is the best initialization scheme. It may differ from problem to problem. So you just so this is a good place to start. So there are various other initialization schemes available. You can look at HC initialization scheme. There is JVR, and there are a few others. So this is Lekun initialization and so on. So this is it about initialization. And anything to ask about initialization? Okay. And the last part was batch normalization. So before going into batch normalization, you must have you must remember the mini SGD algorithm, right? So what was mini SGD algorithm? You basically have say say you have 10,000 training data, and of course you cannot suppose your machine is not that powerful, you cannot train your model with these 10,000 data at the time. Also you cannot use SGD because SGD has very noisy gradient problem. So what you do is you create chunks of say in this case let us say you create chunks of 1,000 points. Say the first 1,000 points is in the first chunk, the second 1,000 points are in the second chunk, and so total there will be 10 such chunks. And then you train your model on each of these chunks. So first of all you pass this chunk to your algorithm, right? And then you pass this chunk and so on. So this was your mini SGT algorithm. Now the problem here is that because you are creating many chunks, the distribution of data in each of these chunks may not be same, right? So by that what I mean is that suppose I look at this chunk, and suppose I say that the data, the mean of this chunk is say 10. Suppose mu here is 10 and my variance in this case is say 20. So if it is a Gaussian distribution, so it will be like something of a 10 here, and then it will be something like this. But when I look at this chunk, the second chunk, suppose my mu in this case is 5 and my variance is say 10. So so if we look at the same curve, it will be like 5, and then it will be something like this. So for different chunks of data, it may have different statistics. So each of these chunks will have its own mean, each of these chunks will have its own variance. So that is very problematic because you cannot say anything good about the data, right? So you are trying to learn something about the data, but unfortunately your data has been divided such that for some portions you are learning with a different type of data, for another portion you are learning with a different type of data or different distribution of data. So that does not work well, or that does not lead to good learning training algorithm. So What this batch normalization do is you take each of these batches. So that is how the term comes here, batch normalization. So each of these batches, and you center each of these. So by center, I mean you make sure that for each of these batch, the mu is 0 and your variance is 1. For batch 1, it is this. For batch 2, it is this. And similarly for all of the other batches. Right? So now you have some very beautiful looking data. So you have a uh, uh, not you have the first batch which has mean 0 and variance 1, your second batch which has mean 0 and variance 1, and so on. So now your algorithm behaves uniformly for each of these batches. So this is where the concept of batch normalization comes in. So this normalization term is basically you have some x here, right? So suppose my output is some x, right? So you subtract the expectation or the mu of that x or the batch that you have, x batch, and divide it by the sigma batch of that. Sigma. So you apply this transformation to each of these batches, and then what you get is each of these batch behaving very well. And by very well, I mean each of these batch behave as if it is sample from the same Gaussian distribution of 0 mean and 1 unit variance, and the model learns does not have any such problem. So there is another issue which says that okay, I want my data to be come to behave well, that is it comes from the same distribution, but also in some cases it may happen, say uh, for suppose you're doing a 10 class classification, right? Suppose you have 10 classes, but each of these classes may have different distribution. Say out of say 10,000 data points, right? Say you have 1,000 points of class 1, 500 points of class 2, and so something may have 100, something may have I don't know, 5,000. So each of these distributions may be different for each of these class. So we don't want each of them to be of the to have this unit norm and sorry unit variance and zero mean. We keep this mean and variance as learnable parameters. We make those parameters as part of the training. So your training will have your weights, it will have your biases, and also it will have these batch normalization layers which will learn this mu and sigma that they have. So this is also another heuristic that that works really well for convolutional neural networks. I think it will be covered in the next 2-3 classes, I think. So yeah, any question from here, batch normalization or anything discussed? So these are the 4 topics that were discussed this week. If you have any more questions, we can discuss this.
Difference between regularization and normalization.
Okay. So regularization is basically you are you're saying that I don't want. Okay, let me give an example. So you have this some non-convex loss function. So regularization says is that I want my weights to lie in this area maybe. So these are your sorry. So these are my weights, and I'm saying that I want my weights to lie in this area. I'm restricting it to say that I only want to look at weights which lie in this area. I don't care what happens when weights lie in this area or this area. So that is regularization. So regularization is it depends on the type of regularization you have or the type of need that you have. Depending on that, you will impose certain constraints on your problem and say that, okay, I don't want to search over the whole weight space. I only want to search over a certain specific certain specific space, and I want to minimize the function only in that space. So if you see, if there was no regularization, this would have been the optimal weight, right? Because the loss is minimum here. But since we are using regularization, I'm looking at only this part of the uh, weights, and I say that my optimum comes at this point. Normalization is something else. So in the context of Gaussian distributions, so whenever we're talking about Gaussian distributions, we need two things to describe the distribution, right? We need the what is the mean of the data and what is the variance of that data, which is standard deviation is sigma, right? What is the spread of the data? So normalization basically says that instead of having this some arbitrary mean mu or some arbitrary variance sigma, I just shift the data such that my mean is always at some point 0 and my variance is always 1. So you something like this.
So
My variance is
regularization we are doing to go to the minima and its loss function plus some other factor. And this normalization is for what? Like, is it also for reaching the minima?
oh no. So yeah, regularization is basically how you define your problem, how you want to minimize your problem with some added constraints. Normalization is how normalization basically says you want to make your data look good. You don't want your data to have some arbitrary shape. You want to say that my data comes from a normal distribution, because the normal distributions are very easy to work with. We say that my data comes from some normal distribution, my data or my values come from some normal distribution with zero mean and one variance. So this process is called normalization. So this is basically to make your data look good. That is it in some simple terms.
So data means the X input we are giving. So
If you
normalization is for the input.
so yeah, it is for the input, but also when we are talking about batch normalization, we are talking about applying a batch normalization at each layer. So you have your input layer here, but you also have these hidden layers, right? You have these hidden layers, and because the weights are random, so this output of these hidden layers are also random. So each of these will have some distribution. Each of these hidden layers will have some distribution, and then you have the output layer. And I say that I uh, put a batch normalization layer after each hidden layer. I put a batch norm layer after each hidden layer such that the distribution that we get after this hidden layer is also from a standard Gaussian distribution, normal zero mean and one variance distribution. So normalization can be given any data, you apply normalization on that. So you can also apply it on the hidden layers also, which is what batch normalization does.
Okay, then there is another broad term, standardization. What is that?
Hmm. So standardization is also the same thing, in the sense that we want our data to have zero mean and unit variance, but that is usually given to the data as a pre-processing part. So given some x, because you collect
You are
data
saying
from,
standardization and normalization are same.
so the term that I'm using here, the normalization in this case is same as standardization. But if you go to sklearn, they have something called the normalization, which is completely different. So I am talking about normalization of a Gaussian, in the sense of Gaussian distribution. So this is to be correct, technically correct. This is normalization of Gaussian distribution. But if you go to sklearn, there is a library in Python. So their normalization just means that normalize, there is this thing called normalize. So you are given some vector x, so you make the two norm of that vector equal to 1. So the normalization in that case is, it is very different from the normalization of Gaussian distribution in that case. So this concept that to use here, that is in sklearn, that is referred to as a standardization. So
So
given,
this normalization that you have written x2, this is for like L1 norm, L2 norm, that way, this normalization.
this is for L2 norm. So basically it
Okay.
says that all of your data lies on this circle or some ball. Radius of this is 1. All of your data lies here. So each of these has length 1 here, right? So my first data point is here, second data point is here, third data point may be here, and so on. So this scalar normalize function works in this way. But the normalization that I'm using in batch normalization, that is basically normalization of a Gaussian distribution. So that basically it says that your mean and your variance are 0 and 1. So these are two different terms. This is normalization of a Gaussian distribution, and this is normalization of vectors. So, so that does it answer the question, or is something not clear?
So standardization is different.
Oh, okay. So scalar also has standardization. So standardization is same as normalization of Gaussian. So given some x, for each feature it will subtract its mu, and for each feature it will divide by the standard variance. So after this you will get some x bar. So this x bar will have zero mean and unit variance, which is similar to normalization of Gaussian distribution. But the thing is that this x bar may not be a Gaussian distribution, just that your mean and variance are within some good, are 0 and 1 basically. So these are used as pre-processing for, because your data you are using data from the natural real world, right? So that may be noisy, that may have very large spread or so on. You want your data to look good so that your algorithm is good. So that is why you use these pre-processing steps such as standardization or normalization, and then you start to train your neural network. So whenever you're trying to run some algorithm, implement some algorithm, you should use these steps. Is there any more doubt?
The dropout regularization, in that like the weights are updated, though we are removing the nodes, their weights are updated.
Yes, yes. So dropout. So dropout regulation basically says you have your different layers and so on. With some probability, this thing may not be there. With some probability, these two neurons, suppose these two neurons are not there. So now your neural network flows only through these many neurons that they have. And whenever you are doing backpropagation in this epoch, so it makes a note that during this epoch, these neurons were not present. So it will only backpropagate through these neurons. It will backpropagate to this and through this. It will not update the weights for this and this. But for a different epoch, because these are all probabilities, some other neuron may be left out. Suppose this neuron is removed in the next epoch and this neuron remains in the next epoch, so then the weights of this will not be updated in that epoch, the weights of this will be updated. Is that clear?
Yes, like if the nodes are not there, why are we updating the weights?
Oh no. So we're talking about, so let us talk about mini batch here, right? So suppose during the first batch, two neurons are not present, right? So whenever you are doing back propagation there, those two neurons, the weights for those two neurons will not be updated. But now, suppose now let us say that the second batch goes in, because dropout is basically a probability, right? We are just tossing a coin and saying whether this neuron is present or not. So suppose the two neurons which are not present in the first epoch or the first iteration, suppose those two are present during this iteration and some other node is not present during this iteration. So the previous two neurons which are not updated in the first iteration, they will be updated during this iteration. But a node which was updated in the first iteration is not present in the current iteration, and that will not be updated in the second iteration. I don't know if this is if the explanation is clear or not. So dropout is
Yes,
basically it's clear, right? So if it
yes.
is involved in the training, it will be updated. If it is not involved because of this probability, it will not be updated. But since this is a probabilistic thing, it will some neuron may be present in one epoch and it may not be present in another epoch. So it will be updated a few of the times. It will not be updated the other remaining times.
So if we are updating the weights anyway, then what
Uh,
is the like use of dropout?
Okay. So for that, so I think last week we looked at these ensemble methods, right? So ensemble methods say that given some data, suppose I train it, so I use different, so I'm not talking about neural networks now, I'm talking about other machine learning algorithms. So there is something called SVM, there is something called logistic regression, and there is something called, say, I don't know, decision trees. So given the data, I train three different models. I train an SVM model on it, I train a logistic regression model on it, I train a decision tree on it, and then I get some outputs. Say, suppose I get O1 here, I get O2 here, and I get something like O3 here. So if we only use one, so suppose we are using only this SVM, so don't need to know what SVM is. I'm just saying this is some name of some algorithm. So if we don't have these two, I will just output O1, right? And O1 may not be a good output. So what we do is we train three different models, we get three different outputs, and then what I do is I output the mean of these three outputs. I take the mean of 0, 1, sorry, O1, O2, and O3. And my final output is this case. So this is an example of ensemble methods. So you train many models and you take an average of this. So on one intuition for this is that if we have to make some decision, you take the feedback from various experts instead of relying on just one expert. You combine your information from the output of various experts and you aggregate that and take that as your decision. So the same thing happens for neural network. Because training neural networks is very costly, and we don't want to train uh, many neural networks for the same task. So we do the dropout regularization. So suppose so my first layer has three, second layer has say four, third layer has three, and then two and one, say. And suppose during the first iteration, my these neurons are not there, right? So now my neural network becomes it has three input, three on the hidden, one, two here, one here, and one. So this is my first iteration neural network, right? So suppose in the second iteration, I don't have second iteration. How do I show this? So for the second iteration, because these are probability, where for each neuron you are tossing a coin and you are just saying whether this neuron is present or not. So for the second iteration, say these and these are not here. Uh, this is not here, and say both of these are here. So now my neural network becomes second iteration. My neural network becomes three hidden layer here, two hidden layer here, two here, two here, and one. So you see, these two are two different neural networks, right? Even though the architecture, initial architecture was same, but because we are doing dropout regularization, you have two different neural networks. See, you have three here, two here, one, one. You have two, two, two here. So this is same as saying you are training us. So you are training a neural network here. You're training a different neural network here, and then finally we'll combine the outputs of all these neural networks. So this dropout regularization is, it helps to implement this idea of ensemble methods for neural networks. Is this example clear?
Yes, thank you.
Okay. Yeah. Any more questions from this week, previous weeks?
So when this recorded session will be available, sir?
Yeah. Can you repeat? Can you repeat?
So when this recorded session will be available on this notes?
Oh, these recorded sessions are updated in the. I think you must have access to that weekly Excel sheet, right? So these are shared there, so you can access the recorded session there. So today is the 8th week, so you can against my name you will find this. You will find this recorded session. It is there in the sheet.
So, sir, kind request, can you, means after the session, will you upload this session?
Yeah, yeah, sure, sure. I will upload it within half an hour after this session ends.
Okay, sir. Thank you very much, sir.
Thank you. Any more questions regarding this or regarding the assignments that you have? You can discuss it.
No, so we can leave, like otherwise the session is over.
Yeah, so we covered the topics that were done in this class. If you have no more doubts, then yeah, you can leave. Thank you. Yeah, sure. The videos will be uploaded in the YouTube link.